Hi everyone, welcome to another video for research design and analysis. This is our first video in our series introducing statistical power. So we've talked a little bit about statistical power in the past when we talked about null hypothesis significance testing. In this module, we're going to delve into it in a little bit more detail, talking about it conceptually in this video and then doing two kinds of applied videos where we actually show you how to calculate statistical power for some simple designs using free power analysis software. So first of all, as a reminder, what is statistical power? Well, we can think about statistical power as kind of a foil to our type 1 error rate in a null hypothesis significance test. So under our kind of traditional null hypothesis significance test, right, we're going to assume some null hypothesis where we say that there's a value for the true mean or true slope in some population, and commonly we say that the true value is 0. And assuming that the true mean is 0, then we're interested in the likelihood or the probability of observing the data that we did if that null hypothesis were correct. Okay, so when we calculate a p-value, we're interested in the probability of observing data as extreme or more extreme as what we observed, assuming that the null hypothesis was true. So for instance, in the case of a one-sample t-test, we might just be interested in the probability of observing a particular mean. We can calculate how far away that mean is from 0 in units of the standard error to get a t observed value, and then we can calculate the probability of that t observed for a given t distribution with the appropriate degrees of freedom. And in this case, right, if we did a one-tailed test, this is at the 2.5 percentile. And if we did a two-tailed test, then that p-value gets multiplied by 2, right? Because the two-tailed test puts an equal probability in each of the tails. So, depending on the type of test that we ran, we'd get slightly different p-values. But assuming we set our type 1 error rate at 0.05, either of these results would be considered statistically significant. So power has a strong relationship to this, in that power is then the probability of detecting an effect, right? So declaring an effect statistically significant, given that the effect is really there. But when we talk about a real effect, that's usually some kind of approximation. So we don't have direct access to what the real effect actually is, so calculating statistical power is always an approximation. It's never a perfect calculation. So when we do this statistical power calculation, it's going to be informed by past work in some way to say, on average, we think that when we do this kind of manipulation, this is the size of the effect that it creates. Or it might be motivated by some kind of minimal clinically important difference. So these things would be like, you can think about if I want to be able to detect a change in pain of plus or minus 1 point versus a change in pain of plus or minus 10 points, right? 1 point is more subtle. So my ability to actually detect a 1 point change in people's ratings of pain probably is going to require more reliable outcome measures, more subjects in my sample, right? It's generally going to be harder to detect that 1 point change than it is a 10-point change. However, a 1 point change also might not be clinically meaningful, so I don't know that I need to invest the time and the energy to be able to detect a 1 point change. If we can say, if there's past research that says in this population a clinically meaningful change is 5 points, then I know, well, I need to be able to detect at least a change of 5 points, because anything less than that maybe isn't worth the additional time and energy trying to collect anyway. So whatever way you ultimately arrive at this estimate, there's going to be some kind of smallest effect size of interest that you're trying to determine. And you're going to assume that this is representative then of the smallest real effect you might be interested in this situation. Now, there are a number of assumptions that are going to go into that calculation, and our power analysis is only as good as the underlying assumptions. So this is one thing I want to reinforce with respect to statistical power. It is a very important concept, and I think it's very important to pay attention to when you're designing your studies, but statistical power is not without its faults, nor is it free from criticism. And I think one very obvious thing that you'll see probably as we go through this is that you can always hack your way to making it look like you have good statistical power. If you make very liberal judgments about what effect size you're trying to detect, right? Or you say, well, what if I assume that the correlation between time points is really high? you can kind of poke your way to getting a statistical power analysis that looks pretty good and tells you can get away with maybe having fewer people in your study than you might really need. So the thing I would say is just be upfront about that. Recognize some of the flaws and the limitations of statistical power, and just be very honest with your assumptions and say, well, this is the best data that we have to go on, so this is what we're going to do. Alternatively, as we will also talk about, sometimes you can't get the ideal sample size. So you're just going to have to say, this is the sample size we could get. Now let's be upfront about that as a limitation and say, given that we could only get 10 people, what kind of effects did we have the statistical power to detect? But let's delve down on this a little bit further, right? So we said that statistical power is the probability of finding an effect, right, in the sense of declaring it statistically significant, assuming that some true non-zero effect exists. So we've already talked about a null distribution, right? So our red distribution, where we say, let's assume the true value is 0, and then the data, if the null hypothesis were true, would fan out in either direction based on the standard error. To conduct a power analysis, we're going to have to assume some specific alternative. So we're going to try to create a point estimate based on the smallest effect size of interest. So in this case, let's say that it's a mean value of 0.5. So we're going to have a blue distribution for our estimated distribution saying, okay, now if the true value were 0.5 instead of 0, how would sample means be distributed? And we can now contrast these two sampling distributions. One, assuming that the null hypothesis is true in red, and one specific case of an alternative hypothesis, assuming that the null hypothesis is false, shown in blue. So in order to calculate power, the first thing that we need to do is say what our type 1 error rate is, right? What was the alpha level for making these decisions? Because remember, power is the probability of finding an effect to be statistically significant. So where we put that alpha threshold matters. Most of the time, right, we put alpha at 0.05. So let's assume that we're doing a one-sided test in this situation. So that would be right at the 95th percentile of the red distribution. And what we're saying then is if the null hypothesis were true, 5% of that red distribution is to the right of the alpha level. So we have a type 1 error rate of 5%, because if the null hypothesis were true, we'd be getting false positives, denoted by the FP, 5% of the time. Following up on that then, we can see, all right, so if we have the rest of the red distribution would be our true negatives. So if we set alpha at 5%, 95% of the time, if the null hypothesis were true, we'd be getting true negatives. However, the problem is the null hypothesis might not be true. So the other thing we need to worry about is our number of false negatives. And in that case, that would be the proportion of the blue distribution that's below that cutoff point. And in this case, we have a pretty big chance of making a type 2 error, right? A false negative error. And actually, in these two distributions, that works out to be a beta, right, or a type 2 error rate of about 93%. So that's not great. That means we are very likely to make a false negative if this was the smallest effect size of interest. So what that translates into then in terms of statistical power is 1 minus the type 2 error rate, or 1 minus beta. Our statistical power, which is the likelihood of having a true positive and declaring it statistically significant, is only about 70%. That's very small, all right? We only have a 7% chance of correctly identifying a real effect as statistically significant in this situation. So that would be bad. So we want to try to design a better study than this and actually set ourselves up to detect an effect, assuming that it's there. And that's the important point about power analysis. Yes, it has limitations, but it's going to force you to think about what kind of effect are you trying to detect, and are you designing your study well enough to be able to detect that effect, right? We don't want to rely on running underpowered studies all the time, because that's going to cause a lot of false positives, and we're going to miss a lot of studies that are actually there, right? Among the things that are declared to be statistically significant, if we're severely underpowered, an awful lot of them are false positives. The true positive to false positive ratio isn't good here. So what we would really like to do is be able to design our studies well enough to push more of this blue distribution onto the other side of our alpha level. So ideally, right, we want our studies to be really well powered, and a common desired level of statistical power is 80%, which translates into then a beta, or a type 2 error rate of 20%, because power is 1 minus beta, so too then is beta 1 minus power. right? But so we want 80% statistical power, which means we would want 80% of this blue distribution to be to the right of this type 1 error rate, or alpha level. Now look at our ratio of true positives to false positives. It's way better, right? We have many more, vastly more true positives in a well-powered kind of universe compared to the number of false positives. False positives are still going to happen. Having good statistical power doesn't make you immune to false positives, but the balance between these two types of decisions is much better, and in general, we're going to be making the correct decision much more often. So, why don't we always just set, power to 80%? Well, there are some limitations here, and the key thing is going to be it's hard to get 80% statistical power in a lot of situations. So we have to think carefully about what we're setting our alpha level to and what we're setting our statistical power to. So if we assume the conventional alpha level of 0.05 and a conventional statistical power level of 80%, that means we are implicitly treating type 2 errors as about 4 times more acceptable than type 1 errors, because we're saying, well, we're comfortable with a 20% chance of a false negative, but only a 5% chance of a false positive. And you can think about that as a fairly reasonable trade-off in a lot of situations, because if we get a false negative, it's important to remember that when we get a non-significant p-value, we don't say there is no effect, but we did not find evidence of an effect. A non-significant p-value is not evidence of no result. It's just an equivocal result. There could be an effect there, but we failed to detect it. And one of the reasons might be that our study was underpowered. And in science, then, generally, it's going to be easier to say, well, this is kind of equivocal. Maybe more data need to be collected. More experiments need to be done with this 20% false negative rate. We're more worried about a false positive error where, if we say, aha, this is an effect and this is real, then perhaps people investigate it and they spend time and money and resources following up on that false positive result. And that's a waste of resources. Or, at kind of the later stage of clinical research, maybe if you find that something has a statistically significant effect, you start, working with the FDA to put your drug into practice, or you make some decision that influences policy. If that ultimately all comes back to have been a false positive decision, that's a really costly error to make. So we're generally going to be more concerned about the alpha level than we are the beta level. So we'll keep it a little tighter at 5%. And in contrast, the beta level is a little bit higher at 20%. However, the optimal alpha to beta ratio is largely going to depend on your research question and the relative cost of these errors. In some situations, a false negative error might be a lot more costly. And then you're going to want to really increase statistical power. In other situations, right, it maybe there's a trade-off in the other direction, and you really want to increase your alpha level because the cost of a false positive is even greater than the conventional 5% level. So the optimal balance between these two is difficult to determine, and many people will have different opinions on this. But the thing that everyone agrees on, and is important to remember, is that these two things trade off, right? Our alpha level and our beta level are going to trade off. Because if I have the line here at that 80% statistical power, 5% type 1 error rate, if I move it to the right to try and be more conservative and drive my type 1 error rate down, right? So now I have an alpha of 0.01 or 1%. That's going to have a negative effect on statistical power. Given holding everything else constant, if I'm more conservative with where I place the cutoff for statistical significance, I have less power. If I go the other way, right, and I'd move this 5% ratio to be more liberal, and I say, well, I'll allow more statistically significant results. I'm going to go from 0.05 to 0.1, right? So now I have a type 1 error rate of 10%. Now I have increased my statistical power. So that's potentially a good thing, but we have to remember that you've also increased your type 1 error rate at the same time. So kind of the optimal point to place that line depends on the balance of type 1 and type 2 errors in your field, and not everyone will agree with you on that. But the point of bringing up statistical power in your study design is to think very carefully about what you think the appropriate type 1 error rate is and what you think the appropriate type 2 error rate is, and then designing your study to have adequate statistical power given the level of significance that you're going to use. So I hope that helps kind of refresh you on some of the ideas of statistical power that we've talked about in the past. And in the following videos, we're going to discuss two approaches to statistical power in more detail. We're going to apply this in the next video to both an independent samples t-test, and then in the video after that to a one-way analysis of variance. But in both of those cases, we're going to go through an a priori power analysis and a sensitivity analysis. In an a priori power analysis, you enter the desired level of power, your alpha level, what you think the true effect size is, and then it's going to solve to tell you the sample size you need to detect that effect. In a sensitivity analysis, however, we kind of flip that around and we say, here's the number of people we can get, right here, or here's the number of observations that we can get. Here's the alpha level. Now tell me what level of power I can actually achieve for different kinds of effects. So to lay that out in a little bit more detail, right, in a classic a priori power analysis, right, done before data are usually even collected, we're going to make some choice about what we want our alpha level to be and what we want our beta level to be, right? These are our type 1 and our type 2 error rates. Then, using some past literature or some pilot data, we're going to make some kind of assumption about the variance. How variable do we expect these data to be? What do we expect the standard error to be? Then we're going to have to make some assumption about the effect size. And this might be, a cumulative effect size based on a meta-analysis of past work, or it might be some minimal clinically important difference that we find in the literature. In either case, right, we're going to establish some smallest effect size of interest and relative to the variance. Then we'll combine that with our choices for the type 1 and type 2 error rates, and then it will tell us the size of the sample we need. And so, it might say, well, you need 120 people in order to reliably find a difference of Cohen's d of 0.5, given your statistical power of 80%, right? In a priori power analysis, we solve for the sample size by fixing these other values. In sensitivity analysis, we solve for the effect size that we can detect by fixing these other values. Again, we make a choice about our type 1 and our type 2 error rates. We make some assumption about the variance we expect based on, pilot data or past research. And then we make some assumptions about the sample sizes that we can detect, maybe based on the cost of enrolling participants in the study, the cost of collecting the data that we're trying to collect, just our historical ability to bring in patients with a particular condition, right? There are many things that might affect that, but we're going to make some assumption that our sample size is fixed. Then, given all those variables being fixed, we can say we reliably have, 80% power to detect effects of a certain size. So sensitivity takes your sample size as a constraint and then tells you what statistical power you were able to achieve for given sample sizes.